Hi everyone, welcome to our fifth lecture. This lecture is on vectors and it is for both the calc and non-calc students. There's no calculus in this lecture and there's no need for any calculus, okay? We've finished 1D kinematics and we're going to move on to 2D kinematics. But before we do, I have to introduce a new mathematical structure known as a vector, because in 2D kinematics, all the kinematic quantities, such as position, velocity, and acceleration, turn out to be vectors, okay? And so before we can jump into 2D, we have to understand the mathematics of vectors. All right, so let's go back to 1D kinematics. And in 1D kinematics, you had position, velocity, and acceleration. And if I ask the question about the direction of, say, the velocity or the direction of the acceleration, that was answered by the sign, okay? And so depending on how your coordinate system was set up, that is, depending on where you put the ruler, the negative was, say, to the left, and the positive was to the right, okay? Or conversely, if you're doing something vertically, we did positive up and negative down, okay? Those are the only two possible directions in 1D. Because you're on a line, either you're going to be going to the right on that line or to the left, okay? You don't have any other possible directions. But 2D, which basically means like a plane, you have an infinity of directions, because if you're at a particular point, yeah, you can go to the right or to the left, but you can also go at any angle that you like. You can go, suppose you're at the, like you've got the points of a compass. You can travel west, you can travel east, but you can also travel north, which is, perpendicular to both west and east, or you can travel south, or you could travel in northwest or northeast or southwest or southeast, and then you can even go further down. You can go north by northwest and north by northeast and west by northwest and so on. And I won't go through all those possibilities, but I think you can understand that if you're in a plane, like just on a flat ground, and I tell you to travel 5 meters, you're going to say, well, which way? Because I could travel 5 meters that way, I could travel 5 meters that way, I could travel 5 meters towards you, 5 meters away from you. I mean, there's an infinity of possibilities. And so in 2 dimensions, it turns out that you need 2 numbers to specify either the position, the velocity, or the acceleration, okay? And because it's 2 numbers, it's 2D. Now, we're not going to study 3D in this course, but if we were to move on to 3D, then it would have to be 3 numbers, okay? And we do live in 3-dimensional space, so that would be physical. Physicists like to, look at abstract spaces, even such as 4 and 5D, and the integer like 4D would mean that you would require 4 numbers to specify a position in 4 dimensions, and so on, okay? So we're only going to go up to 2D, and so you're just going to need 2 numbers, all right? And the question is, how do you specify those 2 numbers? It turns out that there's actually many possible ways that you can come up with some prescription for how you obtain the 2 numbers for 2D, and we'll look at those in a minute. As I said, if you've got position, velocity, or acceleration, you have to have these 2 numbers, and these 2 numbers are paired together, are called a vector. So that's what a vector is. It's a pair of numbers which specifies a position in 2D. All right. There's still time. So if you remember the equations that I gave you for 1D kinematics, there was time in there. Time is still just 1 number. Okay. And so whenever you just need 1 number to specify some physical quantity, we call that a scalar. When you need 2 numbers to specify a physical quantity in 2-dimensional space, we call that a vector. Okay. Now, I just said that there's many different ways that you can come up with how you obtain those 2 numbers to specify, say, a position in 2D. And it actually turns out to be an infinity of ways. Well, we're not going to study just general coordinate systems in 2 dimensions. We're just going to study 2 coordinate systems. These are the 2 typical ones that are used, okay? And they're fairly intuitive, all right? One of them is called Cartesian, and the other one is polar. So, you have Cartesian vectors and polar vectors, all right? And what this word Cartesian vectors means, it means that there's a certain way of interpreting the 2 numbers that are part of the vector such that you wind up wherever you want to go for the position, okay? Well, let's start off with polar coordinates. Let me show you how they work. And so what you're seeing here in my diagram is an x-axis down here, and a y-axis here. So the plane of the page here, or in this case a PDF, that plane, that's your two-dimensional plane, okay? And x is here to the left and right and left, and your y-axis is up and down. All right. Now suppose we have a point somewhere in this plane. We'll call that point P, and I ask the question, where is P? And I expect you to answer that question using a polar scheme, polar coordinates. To get me there, you have to give me those two numbers. Here are the two numbers that you got to give me. One of them is r, okay? R for the radius, and that is the distance that the point P is from the origin. So here's P, here's the origin, and say P is 3 meters from the origin, then r would equal 3 meters. That tells you how far you have to travel from the origin to get to the point P. But just telling you that you have to travel 3 meters is not good enough, because if I say, it's like 3 meters from the origin, you're going to say, well, 3 meters over here, or 3 meters over here, or 3 meters over there, or 3 meters over there. I mean, I gave you a diagram here so you could see where P is, but imagine you don't have a diagram, and I just say 3 meters. It's 3 meters from the tree. You're not going to know, or from the origin, you're not going to know where that is, and it actually just r by itself would specify a circle. So what's that other number? The other number is the direction that you want to travel 3 meters. And this is the angle theta in there like that. Okay. Now theta, there's lots of angles in there. For instance, there's an angle in there. There's an angle over there like that. The way we define theta, it is measured from the positive x-axis. So here's the positive x-axis right here. It's measured from the positive x-axis, and it's measured counterclockwise. Okay, so you start from the positive x-axis and you turn until you get to the direction that you have to travel in to get to the point P. And just as you see in the diagram there, that's how theta is measured. All right, now without proving it, I think you can see that, if I tell you r and I tell you p theta, you're going to find a unique p. Okay, so I say, travel 3 meters at 30 degrees from the x-axis. You're going to say, okay, I got to travel 3 meters, and the direction I got to travel in is this 30 degrees here, and I travel 1 meter, 2 meters, 3 meters at 30 degrees, and boom, you wind up at P. Okay, so that's how polar coordinates work. Okay, they give you two numbers, and the two numbers are r and theta, defined as I just specified. All right. By the way, a minute ago I accidentally said tree instead of origin, and that's because in one of your labs you're actually going to be walking in the park, and when you're walking in the park, you're going to use a compass, and you're going to just locate various points in the park and various trees in the park. And the way you're going to do that is by traveling so many meters in a particular direction, and you'll wind up at the tree or rock that you're supposed to find. Okay, and so that's a lab in practicing polar coordinates. All right, so what's next? Well, the other way you could do this is by Cartesian coordinates. Okay, so this is still the same point P, and it's still in the xy plane like that, and there's the point P. But now I'm going to give you two numbers, and I want you to interpret those two numbers differently. I'm going to give you what's called the x coordinate and the y coordinate. Okay, and so you start at the origin, and I give you a number for x, and you're going to travel so many meters along the x-axis. Okay, and then once you've traveled so many meters along the x-axis, you're going to turn 90 degrees, and you're going to walk parallel to the y-axis. That's that dashed line there. See the dashed line? It's parallel to the y-axis. And I'm going to tell you how many meters to walk along the y-axis. Okay? And so you travel so many meters along the x-axis, so many meters along the y-axis, and you'll wind up at that point P. Okay? And I think it's pretty clear that if I give you, a unique value of x and a unique value of y, you're going to wind up at one and only one point P. So P is uniquely specified by the values of x and y. All right, and doing it this way, we call them Cartesian coordinates. All right. Now, if you think about this for a minute, I just gave you two different prescriptions for how to find the point P. One is by telling you r theta, and the other one is by telling you x and y, and they're different, but they should end you up at the same point P. So you're supposed to end up at that point P, and that means that there should be some way that if I give you x and y, you should be able to calculate r and theta. Or conversely, if I give you r and theta, there should be some way for you starting from r and theta to calculate x and y, okay? And we're going to need to do that because in our word problems that we'll be doing in 2D kinematics, I'm going to wind up giving you information, usually in polar. And the reason I do that is not just to be tough, but because experimentally, polar is much more natural in measuring things and specifying kinematic quantities than Cartesian is, okay? However, the formulas are easier in Cartesian. So you'll get the information in polar and you'll have to convert to Cartesian in order to crunch through the formulas. And then once you get the answer, you may want the answer in polar, but you've got it in Cartesian, you may have to convert back. So in the 2D kinematic problems that we're going to be doing, you're going to be forever converting between Cartesian and polar and Cartesian, okay? It isn't that bad, so let's go through that next, okay? So how do we convert between polar and Cartesian coordinates? Well, to do that, I'm going to take both of those diagrams and superimpose them on one another. So here's my point P, okay? The vector is the arrow that starts from the origin there and then goes to the point P, okay? R, that's the length of that, also known as the magnitude of the vector. It's basically the length here. Like how far do you have to walk from the origin until you hit the point P? Theta is the direction in which you have to walk. And remember, it is measured counterclockwise from the x-axis. All right. Conversely, I could tell you x, and so you walk so far along the x-axis, and then turn 90 degrees here and walk it parallel to the y-axis until you get to the point. Okay, and so you've got both of those coordinate systems on top of one another, r theta and x and y. Okay, well, let's go first. Let's convert first from polar to Cartesian because that's the easier way to do that. And if you haven't noticed already, this is a right angle triangle. Okay, so here's your right angle in there. And the sides of the right angle triangle are x and y, and the hypotenuse is r. Okay, so let me remind you how sine and cosine are defined. The cosine of theta is defined as the adjacent, which is x, divided by the hypotenuse. So cosine of theta is equal to x divided by r. And the sine of theta is equal to the opposite divided by the hypotenuse, which in our case is going to be y divided by r. Okay? Now, I'm going to show you those equations in a minute, but remember what we know and what we don't know. Since we're converting from polar to Cartesian, you know I give you r and theta, so that's known, and you want to find x and y, okay? So using those trig identities that I just mentioned a second ago, you can isolate x and you can isolate y on the left-hand side of the equation, and you can isolate r and theta on the right-hand side of the equation, and you get the following formulas, okay? So you know r and theta, and you plug into this formula, and out pops x. And you know r and theta, and you plug into the second formula here, and out pops y, okay? And just remember that the cosine goes with the x component, and the sine goes with the y component, okay? Make sure that you measure theta, you know, starting from the positive x-axis and counterclockwise, and then these formulas will work. If you're in the middle of a problem and for some reason you make a mistake and you don't measure your angle from the positive x-axis, these formulas don't work. So these formulas were derived under the assumption that you're measuring from the positive x-axis. And just to show you here in the diagram, here's the positive x-axis, and you can imagine it like a dial, and the dial starts along the positive x-axis here, and it turns until it's in the direction of the vector, and the angle through which it turned, that's your theta, okay? A common mistake, don't make this mistake, is you might measure it from the y-axis here, okay? And so, like, say this is 30 degrees, then that's what you should use in the equations below. But if you make a mistake and you measure it from there, then you would get 60 degrees, and those equations won't work at all, okay? And so you won't get the right answer, all right? So that was pretty easy. And there's nothing more to say about going from polar to Cartesian than to just use these equations and make sure you measure theta correctly, okay? The Cartesian to polar is a bit more difficult. All right, let's go back to the diagram, okay? So remember, now we're going from Cartesian to polar, and that means that you know x and y, and you want to find r and theta, okay? Now, x and y are part of the triangle, and r is the hypotenuse. And what relates the hypotenuse to x and y? It's the Pythagorean theorem. Okay, and the Pythagorean theorem basically says x squared plus y squared is equal to r squared. Well, we don't want r squared, we want just r, and so just take the square root of both sides and you get the first equation in converting from Cartesian to polar. Okay, r is equal to the square root of x squared plus y squared. By definition, r has to always be positive. You got to watch it whenever you take a square root, because there's usually two square roots. Okay, there's like the positive square root and the negative square root. Okay, and you know, like, what's the square root of 4? It could be 2, because 2 times 2 is 4, but it could be negative 2, because negative 2 times negative 2 is also 4. Okay, but here, because r is always positive, remember, r is just how far do you walk, and so r is always positive. You just need the positive square root. So you know x and y, x squared plus y squared, take the square root of that, and then you get r. Okay, theta is the tough one. All right, and so let me describe how you get theta. Here is theta. All right, remember, you know x and y, and you want theta. Now, a minute ago I said that x over r, that's your cosine, and y over r is your sine theta. Okay, but we don't know r, so we want a trig identity that has just x and y in it. And the trig identity that relates x and y and theta is the tangent. The tangent of theta is equal to the opposite divided by the adjacent, so tangent of theta is y over x. Okay, now that still doesn't isolate theta, because now we have tangent of theta is y over x. And so you say, well, how do I untangle the tangent of theta and just isolate the theta by itself? And the way you do that is with the inverse tangent. Okay, so you should have studied inverse functions when you did, your equivalent of pre-calculus. Okay, and what an inverse function is it undoes what a function does. So for instance, if you start with 45 degrees and you take the tangent of 45 degrees, you get 1. Okay, try that on your calculator. Do tangent of 45 degrees, you get 1. Well, what's the inverse of that? So the tangent takes you from the 45 degrees to the 1. The inverse tangent would take you from the 1 to the 45 degrees. So the inverse tangent of 1 is 45 degrees. Okay, let me say that again. Tangent of 45 degrees is 1. Inverse tangent of 1 is 45 degrees. It's like one function does the exact opposite of what the other function does. And that gives you the inverse tangent. And so here is the formula partially. Okay, I still have to explain this part, but let's just concentrate on this part right now. Okay, theta is equal to the inverse tangent of y over x. Okay, so theta is equal to the inverse tangent of y over x. Now, the problem with this is that, yeah, that works, but it actually only works in the first quadrant. Okay, and you might go, well, why? Why doesn't it work in all 3 quadrants? Well, you'll see that, because I'm going to actually illustrate that very clearly. But before I do, I better remind you what a quadrant is. Okay, and so here I have a picture of the 4 quadrants. Okay, so here's my x, y plane. This is quadrant number 1. Okay, here's quadrant number 2. Here's quadrant number 3, and there's quadrant number 4. Okay, quadrant number 1, if you're looking at theta, is between 0 and 90 degrees. Quadrant number 2, again, just looking at theta, is between 90 and 180. Quadrant number 3 is between 180 and 270. And quadrant number 4 is between 270 and 360. Okay, now, if you want to identify the quadrant you're in and all you have is x and y, you can still do it. In quadrant number 1, both x and y are positive. Okay, in quadrant number 2, x is negative, but y is positive. In quadrant 3, both x and y are negative, and in quadrant 4, x is positive and y is negative. Okay, so it's pretty easy to identify which quadrant you're in. All right, let's go back to the formula, and let me just show you how it works before I actually try to justify it. If you're in quadrant 1, just doing the inverse tangent of y over x is enough. Don't add anything. Okay, so this is plus, and then you have 3 choices. And you say to yourself, oh, I'm in quadrant 1, so I add nothing. Okay, great. If you're in quadrant 2 or quadrant 3, you take the inverse tangent of y over x, but then you got to add 180 degrees. And finally, if you're in quadrant 4, you take the inverse tangent of y over x, and then you have to add 360 degrees. And you might be wondering now, well, why does it work this way? Like, why do you have to worry about which quadrant you're in and then add 0 or 180 or 360 depending on which quadrant you're in? And the answer is this y over x part, okay? So let's look at this diagram down here again. And let me pick a very easy number. Suppose x is 1 and y is 1. If x is 1 and y is 1, you're in here. You're in the first quadrant, okay? Then if you do y divided by x, well, you've got 1 divided by 1, you get 1. And the inverse tangent of 1, I just said, was 45 degrees, and you would find that you're up here at 45 degrees. Okay, great. But suppose now that both x and y are negative. So you say x is -1 and y is -1. You're down here, okay? Because if they're both negative, you're in the third quadrant. So if x is -1 and y is -1, you're down here. But in the formula, you're going to do y divided by x. -1 divided by -1 is just equal to 1. And the inverse tangent of 1 is 45 degrees, and you're back up here. But you say, wait a minute, I'm in the third quadrant. I should be between 180 and 270 degrees. And yet, when I do the inverse tangent, I wind up at 45 degrees. And how do I fix that? Well, you fix that by adding 180, and there's the 180. The reason this happens is, I don't want to go into all the details in this course, but the reason this happens is because the inverse function for the tangent is actually what's called a multivalued function. There's different branches in which you could be and do this inverse when you do the inverse tangent, when you undo what the tangent does, okay? And this is part of the theory of one-to-one functions, which you should have studied previous to this class. I don't have to go through that entire theory, but it's sufficient for me to show you that when you do the inverse tangent, if you do the inverse tangent of 1 divided by 1, you get 45 degrees. But if you do the inverse tangent of -1 divided by -1, you still get 45 degrees. But in the first case, you're in quadrant 1. In the second case, you're in quadrant 3. You're on two different branches of this multi-valued function, inverse function. And so that's why on the one branch you have to add 0, and on the other branch you have to add 180, okay? So if you didn't fully understand that, that's okay. But, you know, I didn't want to just throw this formula at you without giving you some explanation of what was going on. And I think you can just see it from the mere fact that when you divide -1 by -1, you lose all information about the two negative signs. And if you lose information about those two negative signs, you lose information about whether you're in quadrant 3 or quadrant 1. And so there's a problem there, and this is how the problem is resolved, okay? And so I told you that going from Cartesian to polar is a little bit more difficult. Well, the r part is easy. It's the theta part that's hard. So let me just give you some instructions about how you would do that. Remember, you have x and y, so what you would do is first identify what quadrant you're in. You can do that because you have x and y, and you just say to yourself, look, they're both negative. Aha, both negative, they must be in quadrant 3. Okay, so first identify which quadrant you're in. If you identify you're in quadrant 3, then what you're going to do is you're going to calculate the inverse tangent of y divided by x, but then you're going to add 180 degrees, and that's your answer. Okay, it isn't that bad. You'll get used to it, and you know, there it is. Okay, so now what? Well, let's do some problems. They're pretty easy problems. Let's start off converting from polar to Cartesian, because that's the easy way to do it. And suppose I tell you that you have a vector, and r is equal to 5 and theta is equal to 30 degrees, and I ask you to convert that to Cartesian. So I give you r and theta. I expect you to calculate x and y. You just use the formulas above, and you know, even though I didn't specify it, it's implicit here that theta is being correctly measured from the positive x-axis counterclockwise. And so over here, you're going to say x is equal to r cosine theta. Just plug in 5 cosine 30 degrees, and if you crunch that through your calculator, it'll be 4.33, and then a bunch of other digits, but we'll just keep 3 significant figures. Okay, and then the y component is going to equal r sine theta, and r is 5 sine of 30 degrees, and that gives you 2.5, and there you go. I sort of sketched the vector out. Okay, so here's my xy plane. All right, the angle in there, theta, is 30 degrees, and you travel 5 meters at 30 degrees, and you will wind up at this point P. And that's the Cartesian way of specifying, sorry, the polar way of specifying the point P. The Cartesian way would be to give you x and y, and if I give you x and y, I'm telling you to walk 4.33 meters along the x-axis, turn 90 degrees, walk 2.5 meters in the y direction, and you will end up at the exact same point. Okay, so there's our first problem. Let's do another one. R is equal to 7 and theta is equal to 135. I sketched the vector out right here. So here's my x-axis. Here's my y-axis. Now I'm measuring 135. That lands me in quadrant 2. I'm going to travel 7 meters at 135 degrees. Be very careful. A typical mistake that's made is you'll just pick some angle and measure it. Okay, you'll say, oh, I want to measure it from the y-axis to there, and that's 45 degrees, and I'm going to use 45 degrees of my formulas. No, that's not how it works. Start always from the positive x-axis, and the positive x-axis from the origin and then to the right. Okay, so start there, and just imagine that the positive x-axis is like a dial that's going to turn, like a dial on a clock or something, the hand of a clock. Okay, and it's just going to turn, and it turns to there, and you say, well, how far did it turn? 135 degrees. Okay, and the x component is equal to r cosine theta. That's 7 cosine 135. That gives me negative 4.95 and more digits. The y component is r sine theta, so that's 7 sine of 135 degrees, and that gives me 4.95 and then a bunch of other digits. And so there it is. There's the x and y component. Okay. By the way, you'll notice that they're the same number, but one has a negative sign. Here's a couple of special numbers that you might want to, special angles that you might want to memorize. Sine of 45 degrees turns out to be exactly equal to the cosine of 45 degrees. If you work that out on your calculator, it's like 0.7071 and so on. It's 1 over the square root of 2. Okay, so just remember, sine of 45 and cosine of 45, they're exactly equal. They're the only time that sine and cosine are equal at 45 degrees. And that's just equal to 1 over the square root of 2. And if you work that out on your calculator, it turns out to be like 0.7071 and then more digits. Okay? All right, and looks like I have another problem here. So r is equal to 4 and theta is equal to 240. So 240 lands you in quadrant 3. Again, don't measure from just any old axis. Okay, so this would be like measuring from the negative x-axis. No, you got to start all the way over here in the positive x-axis and turn 240. So x is equal to r cosine theta. 4 cosine of 240, that's negative 2. Okay, and that kind of makes sense because you're in the negative direction. And then y is equal to r sine theta. That's 4 sine of 240, and that's negative 3.46. And so both x and y are negative. That lands you in the third quadrant as expected. Okay. So there you go. By the way, here's another couple of special angles that you should probably memorize. Sine of 30 degrees is equal to the cosine of 60 degrees is equal to a half. Okay, and you go, wait a sec, this was 240. Where did this 60 degrees and 30 degrees come in? Well, it didn't exactly, except that when you do cosine of 240, there's kind of an implicit 60 degrees in there, and that's actually why you're getting that negative 2 there. See, r is 4, and cosine of 240 actually turns out to be negative a half. Okay, and negative a half times 4 is negative 2. Okay, so things like 60 degrees, 180 plus 60 degrees, which is 240, they'll always be, the cosine will always give you a factor of a half. Okay, same thing with 30 degrees and sine. So if you've got sine of 30 degrees or sine of 30 degrees plus 180, you'll get a factor of a half with either a plus or a minus sign. It's good to see these patterns because on a test, this will prevent you from making mistakes, because if you make a mistake and you go, oh, that doesn't sound right, that doesn't fit my intuition, you'll notice it. It's very easy to punch in the wrong numbers on your calculator. Okay? All right, so enough from polar to Cartesian. Let's do Cartesian to polar. So now I'm going to say, look, I'm going to give you x is equal to negative 3 and y is equal to 4. If I draw that on my xy plane, x is negative 3, so I'm actually traveling in the negative direction along x. And then I turn, and I travel plus 4 in the y direction, and I end up here somewhere in the second quadrant. Okay, so I've given you x and y, and I want you to calculate r and theta. Okay, so r is equal to the square root of x squared plus y squared. That's going to be the square root of 3 squared plus 4 squared, and that turns out to be 5. Okay, and now we need to calculate that angle theta. So theta is the inverse tangent of y over x. Y is 4. You can see it there. X is -3. So the inverse tangent of 4 divided by -3 is some number. But remember, we're in quadrant 2. And for quadrant 2 or quadrant 3, we'd have to add 180 degrees. So that's where that 180 is coming from right there. And this is going to give me, oops, there we go. Sorry, resize the window. So the inverse tangent of 4 divided by -3, that's -53 degrees, plus the 180 is 180, and that gives me 126. And if you look at my diagram again, you'll see that, yeah, that kind of makes sense, because if I measure from the positive x-axis, it's definitely more than 90, it's less than 180, it's about 126 degrees there, like that. Okay, great. Now the next slide is just to remind you about these special angles and the sines and cosines of these special angles. Okay, so just remember that sine of 0 is 0, sine of 90 degrees is 1, sine of 180 is 0, and sine of 270 is -1. We actually saw that when we did the simple harmonic oscillator. Cosine of 0 degrees is 1, cosine of 90 degrees is 0, cosine of 180 is -1, and cosine of 270 is 0. Okay, well, let's see if this works out. Over here, if I'm along the x-axis, directly along the x-axis, what's my angle? My angle is 0. So my x component is cosine of 0, which is 1, which is the first number. Okay, so the x component is the first number in the pair of numbers here. So that 1 there is cosine of 0 degrees, and that 0 is sine of 0 degrees. Okay, and there you are there. Now, what if we're right here? What if we're at this point? Well, now we're at 90 degrees. So if you do sine of 90 degrees, okay, or do cosine of 90 degrees for the x-axis first, x component first, cosine of 90 degrees is 0. There you go. You can see the 0 right there. Okay, and sine of 90 degrees is 1. Okay, when you're over here at that point, that's 180. The cosine for the x component, the cosine of 180 is -1. So you can see that x there is equal to -1. And the y component of 180 is sine of 180. Okay, and that's 0. All right, and you can see that here. And then finally, that point right there, that's 270 degrees. So if you do cosine of 270 degrees, that's 0. So the x component is 0. And the sine of 270 degrees is -1. So that point there is that x is equal to 0 and y is equal to -1. Okay, so why did I show you this? Well, because remember when we did the simple harmonic oscillator, I gave you these special angles. Okay, they're off by 90 degrees. Okay, so 0, 90 plus 90 is more is 180 plus 90 more is 270. Okay, so they go in increments of 90 degrees. Well, though there in that situation, you were at different points along the cycle of the simple harmonic oscillator. Here, when it comes to vectors, we're at different points in the xy plane. Okay, and so 90 degrees apart each one. Okay, so this is just yet reinforces how the sine and cosine work at those angles, 90, 180, and 270. 0, 90, 180, and 270. Okay, and then you should probably also memorize sine of 30 degrees is equal to cosine of 30 degrees, which is a half. And sine of 45 degrees is equal to cosine of 45 degrees, which is 1 over the square root of 2, which is 0.707. Okay, and a lot of my problems I'm going to be using these angles. Okay, so if you have them memorized, then when you do this on your calculator, one, you may not even need your calculator if you have them memorized, but two, it'll be, like I said, confirmation that you didn't do anything wrong when you plugged in the numbers into your calculator. All right, so one more topic in vectors, and that is, how do you add vectors? So why do you want to add vectors? Well, if you travel a certain distance, say even in 1D, suppose you travel 3 meters to the right, and then you travel 4 meters to the right. Well, if you travel 3 meters and then another 4 meters, you traveled a total of 7 meters. You were essentially adding one-dimensional vectors. Now, one-dimensional vector is just a number, so it's like 3 plus 4, okay? But now, we're in 2D, we want to do the same thing that we did in 1D. We say travel 3 meters and then travel another 4 meters to the right, okay? But now, when we do this in 2D, we have this extra infinity of all possible directions. And so I'm going to say travel 3 meters in one direction, then travel in 4 meters in a different direction. And you're going to say, well, where do you end up? And the answer to that is the addition of vectors. That's what we mean by adding vectors. Okay, and so I'm going to do this for you graphically first, and then I'll show you how to do it algebraically. Okay, and you'll actually have a lab on this in which you're going to be adding vectors, and you're going to add them, graphically, and you're also going to add them using the algebra, okay, to make sure that they work out. All right, so graphically, a vector is represented by an arrow. You already saw that, but let me now make it explicit. So if you have an x and y axis here, the vector has a tail, okay, and then it has a head. The head is where the arrow is, okay, and it has sort of a direction because you're walking in a particular direction like that. All right, now if you're adding two vectors, it means that you've walked one vector from tail to head, and then you walk the second vector, which is going to be another tail to head. And so in my next diagram, I've shown you how you add two vectors. So here I have a vector v1. I don't know why I called it v1, but I called it v1. So we have a vector v1, and then we're going to walk vector v2 like that. Okay. So to walk vector v1, we're going to walk 4 meters at 30 degrees, and then to walk vector v2, we're going to walk 5 meters at 90 degrees. And I'm going to ask the question, where are you? Where do you end up? Okay. And I'm trying to show you here in this diagram, you start at the origin, and we're going to walk 4 meters at 30 degrees. Well, that part is easy. Okay, maybe I can expand this just a little bit and so you can see this a little better. Okay, so here we go. I'm start at the origin, and I say, look, walk 4 meters at 30 degrees, and that's easy. And then I say to you, and now walk 5 meters at 90 degrees. Okay, well, the 5 meters part, that's easy. You're going to have to walk 5 meters. But how do you measure that 90 degrees? Because you're not at the origin anymore. And if you look at the way I showed you how to, define theta up above, I always said, I always did it at the origin. From the positive x-axis, but we were at the origin. But now we're not at the origin. We're somewhere in the middle of the plane. So how do you measure the 90 degrees there? And the answer is, just imagine that the positive x-axis is just a direction. Okay, and you can see here, I just drew it here. It's like, if I'm at that point there, which way is the positive x direction? It's always to the right, okay? So if I'm there, the positive x direction is to the right. If I'm here, the positive x direction is to the right. And so wherever you are, you can just add a little tiny, origin there, if you like a secondary origin. And so here you can see I've put this dashed line. That's like my second positive x-axis. And then I'm here. I'm right at that point there. I'm going to measure 90 degrees from there. Okay? So I don't try to measure, 90 degrees down here. That makes no sense. I'm here, and, I've walked the first vector, and I'm about to walk the second vector, and I need the direction of the second vector. So imagine that I have a little temporary positive x-axis going like that, and I go, oh, I'm going to measure 90 degrees from there, and then that'll bring me up. Where do I end up? Well, I end up where I would be after I walk the first plus the second vector. Okay, that's why this is called vector addition. So I walk the first vector, then I walk the second vector, and I wind up at P. Okay, so there you go. That's how you would graphically do this. And it doesn't matter, just like in ordinary arithmetic between numbers, 3 plus 4 is the same as 4 plus 3. It doesn't matter what order you do them in. In mathematics, this is called commuting. Okay, so vector addition commutes. It just means it doesn't matter whether you do v1 plus v2 or you do v2 plus v1. You'll still end up at that point P. So I could have walked along v2 first and then v1, and I would have still wound up at the point P. Okay. So that's graphically how you do it. How do you do this algebraically? So what I'm going to do is I'm going to try to motivate how you do that algebraically. Let me shrink that down again so everything fits in. All right. So here we go. We've got an x-axis here, and we've got a y-axis there. And to make it more obvious, I changed the angle of v1 and v2. The angle doesn't matter. This is arbitrary angles, okay? And so I'm going to walk my vector v1 and end up there. And then I'm going to walk my vector v2, and I'm going to wind up at the point P, okay? Now, how do I determine the x and y components of point P? Well, let's take a look at the x and y components of v1. The x and y components of v1 are x1 along here and y1 along there. Okay, so if I've traveled x1 and then y1, I wind up at that point there. But then I've got v2, and v2 has components x2 and y2. If I'm at this point here and I walk distance x2, I'll wind up there, and then I walk distance y2, I'll wind up there. Okay, but it's pretty obvious from the diagram that the x component of this position right here is going to be x1 plus x2. And the y component of P is going to be y1 plus y2. And so there's our answer. To get the x component of P, just add up the x components of V1 and V2, namely x1 plus x2. And to get the y component of P, add up the y components of V1 and V2, and that's y1 plus y2. Okay? And so there's the formula right here. Okay? So the x component of P is just x1 plus y, the x component of P is just x1 plus x2, and the y component of P is just y1 plus y2. In other words, if you have a bunch of vectors, convert them to Cartesian, to get the resultant x component, just add up all the x components of all the vectors. And to get the resultant y component, add up all the y components of all the vectors. It's that simple. Okay? So let's do an example. I'm going to give you 3 vectors, and I'm going to give them to you in polar. So vector number 1 is 4 meters at 30 degrees, vector number 2 is 6 meters at 180 degrees, and vector number 3 is 4 meters at 270 degrees. Basically what I'm telling you to do is to go on a little trip, to take a little walk. Walk 4 meters at 30 degrees, then walk 6 meters at 180 degrees, and then walk 4 meters at 270 degrees. Tell me where you wind up. Okay? So I tried to show that in a diagram over here. The diagram is a little small, so let me just expand it for a second here like that. Okay. And so here I am at the origin, and I'm going to walk my vector v1, which was 4 meters at 30 degrees. Then I'm going to walk my vector v2, which it was 6 meters at 180 degrees. And then I'm going to walk my vector v3, and I forget what that was, but it was at 270 degrees. And I'm going to wind up here. And it looks from my diagram, this is kind of a rough sketch, but it looks from my diagram like I'm going to wind up in quadrant 3. And so we anticipate that our final answer will have both x and y values negative. Okay, so let me shrink this down again. Okay. The first thing you need to do is, I didn't teach you how to add vectors with polar coordinates. I taught you how to add vectors in Cartesian. But I gave you these vectors in polar, so you say, well, what do you do? Well, you have to convert from your polar to your Cartesian. Okay, so that's the first thing you do. So I take my vector v1, which is r is equal to 4, and theta is equal to 30 degrees, and I go that x1, the reason I put a subscript 1 there is because it's for my first vector. So x1 is r cosine theta, which is 4 cosine 30 degrees. Crunch that through your calculator for 3.46 and more digits. Okay, y1 is going to equal r sine theta, which is 4 sine of 30 degrees, which turns out to be 2. Remember, sine of 30 degrees is a half. 4 times a half is 2. Okay, so that converts your first vector from polar to Cartesian. Okay, then you've got the second vector, which I did down here. Here's my second vector. Okay, and x2, this is the x component of the second vector, is r cosine theta. That's 6 cosine 180, and cosine of 180 is -1, so you get -6. Okay, and y2 is r sine theta. That's 6 sine of 180, which is 0. Okay, so there's my second vector in Cartesian. And then my third vector, okay, which was an r of 4 and a theta of 270. So I go x3, the x component of the third vector is r cosine theta. That's 4 cosine 270, which is 0. And the y component of my third vector is r sine theta, 4 sine of 270, which is -4. Okay, so I converted all 3 vectors into their x and y components. Why did I do that? Because to add the vectors, I need the x and y components. Okay, now that I have the x and y components, all I have to do is, to get the x component of my final position, is just add up the x components of the first vector, the second vector, and the third vector, and just taking the numbers above and adding them together. That gives me a final x, a resultant x component of -2.54 meters. And then a y component. To get the resultant y component, just add up all the y components of the individual vectors. That's y1 plus y2 plus y3. So that's 2 plus 0 plus -4, which is -2. And there you go. There's where you are in x and y components. Okay, so you'll notice, remember, we kind of guessed that we would wind up in the third quadrant, and sure enough we are, because both the x and the y components are negative. And that is the answer. you would be able to end up at your vector if you walked negative 2.54 meters in x and then negative 2 along y. But just for practice, let's convert this now from Cartesian to polar. Suppose I asked in the original question, answer in polar, so you have to answer the question in polar. So you have the Cartesian, convert to polar. To get r from x and y, use the Pythagorean theorem. So r is equal to the square root of x squared plus y squared. So that's the square root of, here was my x component, there's my y component. They're both negative, but when you square them, they become positive. And crunching that through my calculator, I get 3.23 meters, okay? And then to get theta, I use the inverse tangent of y over x. But now remember, we're in quadrant 3, and in quadrant 3 I have to add 180 degrees. And so I'm going to do the inverse tangent of y over x plus 180 degrees, plugging in my x and y components. My y component was negative 2, my x component was negative 2.54, okay? And that turns out to be the inverse tangent by itself gives me 38 degrees. Notice that would end me up in quadrant 1. 38 degrees is in quadrant 1, but we're not. The answer is supposed to be in quadrant 3. That's why we add that 180. So 38 plus 180 gives me 218 degrees. Okay, and there's the answer. The resultant point, that is, after you add up all these vectors, where do you wind up? You end up at r is equal to 3.23 meters at an angle of 218 degrees. Okay, so that's the end of our lecture on vectors. This is a little bit of a mathematical aside because we're going to go on to 2D kinematics in my next lecture. And remember, in 2D kinematics, the position is a pair of numbers. The velocity is a pair of numbers, and the acceleration is a pair of numbers, okay? So if I say, where is this thing? You can't answer it with just one number like we did in 1D. You can't say x is equal to 4. That makes no sense in 2 dimensions. To tell me where something is in 2 dimensions, you're going to have to give me 2 numbers, okay? Whether it's in Cartesian or in polar, you're going to have to give me 2 numbers, okay? And so all of the mathematics that I've given you, there's a lot more mathematics that you could do with vectors, but just the mathematics that I've given you right now for vectors is what you're going to need to do the 2D kinematics for the course. Okay, thank you very much.